So, in this lecture we are going to talk about derivation of discrete time small signal model, and there are two parts. So, this is part 1 and the next lecture we will continue part 2. So, in this lecture we will first talk about effect of perturbation in discrete time modeling, then 0 input and 0 state response, that means what is the effect of perturbation in the initial state and what is the effect of perturbation in both initial as well as the duty ratio, that is the control input, and finally we want to derive the discrete time small signal model. So, first we will start with interval 2 sampling discrete time model. So, this waveform shows the waveform of the interval under interval 2 sampling under trailing edge modulation. So, you can see that at the rising edge of this clock the switch turns on, that means this is the this is not the rising edge. So, at this rising edge of this switching clock actually the switch will turn on. Okay, so, that is why it is trailing edge modulation, and here this waveform, that means this dotted one is the, this is a nominal trajectory, this is a nominal trajectory, So, this is a nominal trajectory, is a current waveform, but you can think of trajectory because if we combine both current and voltage then it will look like a trajectory, and the dotted line is the perturb one. So, perturb trajectory, in this case it is the inductor current waveform, and this amount of perturbation that we have given here is the xn part, and this xn perturbation I would say this different, that means this is the same difference where xn is the initial state at the beginning of the cycle. That means, if we consider the blue waveform, even if we consider whether nominal or perturb, so any of this waveform at the point of this is nt, this is a sampling point, and n plus 1 t, this is also sampling point. So, if we take this sampling point, whether we take nominal or the perturb trajectory, at the sampling point we are talking about x of n, that is the value of the state at nth clock instant, at the beginning of nth sampling instant, and the end of nth sampling instant there will be another sampling. So, that we are talking about x n plus 1. And if there is a perturbation in the initial state, we want to find how this perturbation is getting propagated at the end of the cycle or end of this sampling instant, that interval, and that we call about phi of xn tilde. So, we need to find phi. How to get it? So, let xn is the the state variable, that is the representation at the beginning of the nth sampling instant, and this will start with mode 2 because we are talking about this particular duration the switch is off and we call it as a mode 2. So, this is the duration when it is mode 2, and this is the on state duration which will be mode 1. Again this interval will be mode 2. Mode 2 means the off state and mode 1 is the on state. So, here this duration interval is the Ts and that is the delay. So, we are inserting, that means we are capturing the sample here, and but the actual switching is happening here. So, this delay is provided to accommodate ADC conversion time as well as the controller computational time. So, this Ts is the duration of this mode 1, that is the delay. Then the mode 1 start, and the mode 1 duration is the on time, that is the on time in the mode 1, that is the duration of this interval. Okay. So, duration of this mode 1. Now, then next the rest of the duration, the final time is the n plus 1 t, where we are taking another sample. So, we are talking about the mathematical model between the two subsequent sampling, where the starting value is xn and the final value is xn plus 1. We want to see if the xn we perturb the initial condition, what will happen at the end of this sampling, that means cycle, and we are talking cycle means it is synchronized with the sampling time. So, this for mode 1 the matrix are, because we already know the state space model, for mode 1 the matrix are A1, B1 and C1. What is A1? A1 is the in the state matrix, B1 is the input matrix and C1 is the output matrix. Similarly, for the mode 2 there are A2, B2 and C2. So, how do you So, now we are considering the initial state perturbation, that means this is my xn perturbation, this duration, and we are trying to find this one, that means this one, and this is nothing but our phi of xn. So, here we are not disturbing the duration, that means we are not changing. So, this is like a, in this case, a constant on time, or if it is under pulse width modulation, the constant duration. Then xn plus 1 can be obtained by this. So, first xn propagate through this, and this is my mode 2, and the mode 2 matrix is A2. Then it propagate through the next mode, that is my A1. So, it goes to this, that means this one is now x1 tilde. That means after n we can consider this is my x1 tilde, and it will be propagating through this state, which is A1 T1, and this one we can consider x2 tilde. So, that means we are talking about this is the x2 tilde, and then end of this it will propagate through this matrix, which is nothing but this one, and we will get this end result here. That means we are getting the final, that means the perturbation at the end of the cycle will be propagating through first mode 2, then mode 1, then mode 2, and here we are talking about T1 equal to d into t, because we are talking about pulse width modulation. Okay. And this whole matrix will like phi, because we got xn plus 1 tilde is the phi times xn tilde, and this is presented in this paper. So, you can refer for the details. Next, this initial perturbation, if we consider for leading edge modulation, where the leading edge modulation at the rising edge of the switching clock, actually switch is turned, at the rising edge of the switching clock, if we consider at the rising edge of the switching clock, this is the rising edge of the switching clock, the switch turns off and switch turns on again. So, at this rising edge switch turns off, and the switch turns off whenever certain condition is met. Here, since we are using off time, so under open loop condition we generally fix the on time and off time. So, this duration off time is constant, but if we use any control method, that means valley current mode control, then this off time actually switch will be turned on again when the inductor current hit the valley current. Okay. And this we have discussed in our previous lectures about various architecture of valley current mode, then peak current mode control. Now, under leading edge, the switch, the sample is generally captured during the on state, and that is why it is called interval 1 sampling. That means sample is captured at the on state. Again, we are talking about a perturbation at the initial state, which is xn tilde, and we want to figure out what is the perturbation at the end of this cycle. So, here we can again consider x1 tilde, and here again we are considering x2 tilde, and finally this is our xn plus 1 tilde, and we want to obtain xn plus tilde phi times of xn tilde. So, that is our objective. And again we can follow, it start with nt, that is my sampling time, the age of the sampling. Then in next mode goes to the duration of this mode is the delay, and again this delay is nothing but the delay due to ADC conversion and computational time, and during this mode is my mode 1, that means the on state, and that is exactly shown. This state is my mode 2 when it is off, and again the rest of this interval it is mode 1. So, then if you propagate, again the same, the perturbation first propagate. So, this is my, this one is my now x1 tilde, which I have shown here. Then if I change the color, this one will be my x2 tilde, which is shown here, and then it is propagating to the remaining interval, which is a1 into t minus t of ts, and then you can get the final. So, this is like it is propagating stage by stage, and this is the overall xn plus 1 equal to this, and this is nothing but your phi. So, that means we are getting x n plus 1 tilde to be phi times x n tilde, and this is presented in this paper. So, in this paper, initial perturbation, looking at the waveform, you can actually get this perturb matrix by looking at how they are propagating. Next, we have only considered the initial perturbation, but now we also want to consider the duty ratio perturbation. So, here there are two things. First, you can see the blue one, the first one, the blue one, this dotted line up to this point is my nominal trajectory. Okay, that means this is my nominal trajectory. So, in this case, this is my nominal trajectory, nominal current. Here it is inductor current. And the first thing, if we apply an initial condition perturbation, so this solid line indicate the perturb current, inductor current, it is after perturbation, and here we are applying a duty ratio perturbation. So, it will also get perturbed, and this will introduce an additional state perturbation, this additional state perturbation which will propagate through the rest of the duration. So, this duration perturbation is due to the perturbation in the duty ratio. So, how do you compute the overall perturbation? So, if you zoom this portion, then it turns out that at this time, that means we are talking about this time after the perturbation, this goes to here. So, at this time your state perturbation occurring is due to the perturbation in the duty ratio, and that is captured here, that difference, and this difference is gamma times d tilde, and this difference which was due to the initial condition perturbation is due to phi into x n tilde, and we want to get. So, if you consider only duty ratio perturbation, then this x d tilde can be obtained from by subtracting x 2 minus x 1, and it can be shown by means of averaging a 1 minus a 2 into x p, where x p is the state under steady state, that means for nominal part, and then V in is the also steady state value, and you can get this d in tilde, that is the difference in the duty ratio. So, effectively this is something like some function, that means some constant term into d tilde n, and we will see how to represent this. And this constant term depends on what? A1, A2 matrix, B1, B2 matrix, input voltage, time period, and so on. And these things have been presented in this paper. So, our objective, so this is like a alpha, that means here you are talking about alpha. So, you will get alpha t, that means this perturbation is represented by, because the cause of this perturbation is the duty ratio, cause of this deviation of the state is due to the duty ratio perturbation. So, this can be captured by alpha t times of this duty ratio perturbation, and this is an approximate version, and you can write the overall state perturbation due to. So, if you only consider the duty ratio perturbation only, then x n plus 1 perturbation. So, this is only due to duty ratio perturbation, duty ratio perturbation. So, if you only perturb the duty ratio, then it will cause a perturbation deviation in the state x d, and this state will propagate through rest of the interval. And what is the interval time? So, you see it is actually the effect is coming here. So, you are taking about this. So, this duration is nothing but t minus t1 minus ts, and t1 is actually it is like a capital T1 plus T1 perturbation, which is the duty ratio perturbation, and in this case it is approximately taken as t minus T1 minus Ts. That means it is assumed that perturbation is very small. So, you can get this time here. you can get this time, because you need to have a steady state value, and this is A2 times. So that means this will be reflected as this function. So this is the reflection which is coming due to the perturbation here. It is only due to the duty ratio perturbation. Okay, so it is given here. Now the overall perturbation can be, that means here, since we are only talking about the perturbed trajectory and we are applying some sense of averaging to get this expression. So here the perturbed model becomes a linear model. So we can apply superposition theorem. Why? You can break the final perturbation into two parts. The final perturbation is due to only initial perturbation, that we have seen. The final perturbation due to only duty ratio perturbation, we have seen, and the total perturbation will be sum of these two perturbations, and this comes straight away from the superposition principle. So you can get phi that we have discussed, and you can get gamma from this perturbation, and gamma actually is propagated through only this duration, whereas the initial perturbation happen throughout this whole interval. So that is why for a buck converter, if you consider this A1, A2 matrix are common. So these all matrix for a buck converter, if you consider a CCM buck converter or a synchronous buck converter, where A1, A2 with A1 equal to A2 equal to A. So you will get phi equal to simply e to the power AT. That means this propagator is passed through the entire duration, but this only passed through this duration. So the overall output equation you can write C equivalent into Xn perturbation, and this C matrix for this case, since the C matrix is common for buck, because there is no discontinuity in the output voltage. But if you take a boost converter, then you have to be careful to select this C equivalent matrix depending upon where you are taking the sample. Is it the interval 1 sampling or interval 2 sampling, and you will get a structurally different C equivalent matrix for a boost converter. And that actually also there are research papers, so that C equivalent matrix may lead to some at least marginal effect in the right half plane 0 effect, depending upon where you are taking the sampling. So using approximation, if you approximate, because these functions all are exponential matrix function, but you cannot get a rational transfer function using this, so you have to approximate, and if you approximate, then you will get a rational Z transform. So if you consider the total delay, because we have discussed that tau d, Td, the one delay is due to this, which is this is the delay due to controller computation and ADC conversion, but there is also a delay due to DPWM. Why? Because we will compare that if the analog PWM if you consider and the digital PWM consider. So digital PWM, if you just sample in, and it will hold for the whole cycle. So that means throughout from the starting to the switching time, the signal is not allowed to change. That is why it is introducing a delay of dt. So if you consider this total delay, then you can get the phi and gamma for interval 1 and interval 2 sampling, and whether the duty ratio, this sampling delay is greater than dt or less than dt. Based on that, you will come up with two different form, and what will be phi and gamma, they are presented in this book, you can get detail. So if you talk about a synchronous buck converter, A1, A2 are same, and B1 is non-zero, but B2 is 0. If there is no load, because we are not talking about load sync, then this phi will simply become alpha. So this will be E of AT, because this phi, this all A1, A2 matrix are common. So you can write e to the power, that means A1, let us say some T1 into e to the power A2 T2. In general they are, so in general it is A1 T1 plus A2 T2, it is not in general. Where it will happen? If matrix satisfy this property, if this is valid, if this is valid, if this hold, if this holds, then we can write A1 T1 into A2 T2 is equal to A1 T1 plus A2 T2. So, we can write only when this commutative property is actually is valid. But in case of buck converter, if all A1, A2 or matrix are identical, so if you take A1, A2, which is nothing but A square, so it already satisfied. So, in this buck converter, you add up this all matrix, and since they are in same, so you will end up with this result. Similarly, if you talk about the last one, all A1, A2 are same, so you will get it. And since buck converter A1, A2 matrix are same, so this term will be 0, and this B2 is already 0, null matrix, so you will get only B1 Vin. Okay, so you will get the overall C matrix you already know. So, that means you can obtain the small signal transfer function. So, in summary, we have considered effect of perturbation in discrete time model. We have also shown 0 input and 0 state. That means 0 input means the perturbation due to initial condition only, and 0 state means the perturbation due to the duty ratio perturbation only. And we have also discussed discrete time small signal modeling. So, in the next lecture, we are going to talk about another alternative approach. That means this approach was simple. From the drawing the waveform, you can capture the perturbation effect, but in the 0 state response, you need to apply a little bit of averaging technique to get it. Otherwise, this technique is much more straightforward, and the next lecture we will be talking about by taking in starting with a large signal model, how to directly you can derive the discrete time small signal model. So, I want to finish it here for today. Thank you very much.